All right, it is Friday. Excuse me, and you all just left after we watched that neat video on them doing that surgery with that guy awake. Today, or this last video that I'm going to make is on the Corpus Callosum, and it's going to be fairly quick, but it can be fairly confusing. So just try and stay with me. I may end up confusing myself, but because there's stuff I'm going to skip. But anyways, we're going to go over the Corpus Callosum, and it's Latin for tough body. And what the Corpus Callosum is, you know how you've heard of, I think in the last video I talked about being left-brained or right-brained or something like that. There are certain things that the right hemisphere does, and there are certain things that the left hemisphere does. Well, these two hemispheres are interconnected, all right, and it is interconnected through these tissues here that we call the Corpus Callosum. One common misconception is that people can be right-brained or left-brained. We've already talked a little bit, I think you saw this in the video, how it's pseudoscience. It's not really true because there is a lot of communication that happens between the two halves. Now, each half may specialize in something different, but if I'm walking, the entire brain is going to light up. Here's a short video.
June Wada of the University of British Columbia first injects a dye opaque to X-rays into the artery supplying blood to the left hemisphere. This shows the route an anesthetic will follow when it is injected during the test. A similar series of X-rays, seen from above, shows how the dye, and hence the anesthetic, will flow only into the left hemisphere. It is vital the surgeon confirm where speech is located in each patient so that an intended operation to alleviate epilepsy can be safely performed.
Again, just like in the video we watched in class, they need to know exactly where things are, and somebody's calling me.
The test also shows that the left hemisphere controls the right hand.
Start with go. Now I'd like you to count slow and loud to 10 and back to 1. Don't stop counting.
2, 3, 4, 5, 6, 7, 8.
The left hand remains upright, controlled by the still conscious right hemisphere.
Carry on.
Okay. Carry on counting for us.
Speech gradually returns as the anesthetic clears the left hemisphere.
1.
All right. So again, that anesthetic is very fast working. Went only through one side, and you saw how that works. Something to remember, and this is where it'll get confusing, is that the left hemisphere generally controls things on the right side of the body. So this side of the brain controls stuff on this side of the brain controls stuff on this side. So like here in this video, you can kind of see, although you've got part of the visual field is seen by both eyes, the peripheral vision of the right eye is actually processed by the left side of the brain, and vice versa. Actually runs all the way back here to the occipital lobe, which we talked about in the last video, again, which is back here in the back of the head. Right. So, but that's to realize that the left side of the brain focuses on deals with the right side of the body is going to be important to know, especially when we're talking about severing the two. Because there is a procedure called a split brain procedure. And essentially, in cases of epilepsy, the surgeons essentially cut the corpus callosum in half. And that's where they call it the split brain. Which sounds rough, because remember, there's a lot of connections that happen through there. And then, but what they found is that has not been most people generally will live their lives normally after that, because other than with a drop in epileptic seizures. But under certain circumstances, there are issues, and here's an example of one. What they would do is they would have somebody look in the middle. As you can see, they'd stare at this dot right here, and then they would flash a word or two words separated by a dot that are just projected normally. All right. Now they would only see, and the way it's done, you would see one of two things. They would ask, "What word do you see?" And if they were looking at the right side, they would say art, or they would have point their left hand to the word that they saw, and in this case, they would point to the he. They wouldn't recognize the whole one. Okay, so and again, that's the miscommunication that's happening between they're not talking to each other, both sides. All right, so if she's looking on one side, its brain is interpreting it from the other side. For these patients, life changed very little on the surface, with the exception of far fewer seizures, but put under certain circumstances. However, the side effects were very clear. They might pick up a key, but say ring, again, because the two sides aren't talking to each other. They're not picking up the key ring. Left side's picking up a key, right side is reading ring. So, and these are some examples. They'd stare at the dot and then pick whichever side. What do you see here? Stare at the plus sign. All right. And if they were looking to the right side, they might say, and then let's see. If they're looking to the left side, they would say, I don't know, but they would point or draw to a foot, even though that's on the left side. All right, so again, it's being interpreted by the right, and then the left other hemisphere, ball, same thing with butter and fly, fire or fighter, Bob Ross, or cat. So whenever you split that, there are some circumstances to where when both sides need to talk to each other, it can't. That produces some strange results. Last thing on here is plasticity. You may have heard there's some commercials going around a while back on some sort of online site where you played games essentially, and they touted the idea of neuroplasticity to help you get smarter. It's sort of neuroplasticity is a thing. I don't know if playing those games like that website said it would does plasticity, but we are going to talk about it just for a little bit. Neurons do have the ability to change and to make new connections. All right, and that change in those connections is called plasticity. This means that the nervous system, and especially the brain, has the ability to adapt or modify itself as a result of an experience. And this happens a lot with babies and with young kids. Their brains are changing almost daily with every experience, with everything they learn. The neurons change. They form more dendrites, which make more connections, which sort of helps to formulate the brain and how it works. And, some things work better with practice. Some things without practice stop getting used. That's one of the reasons why once you learn a second language, if you don't use it, those neurons don't fire. They end up getting essentially paired off, or that used for something else that is going to be used. So I'll just give you a life lesson. If you learn a new language, keep using it or it will go away. But the brain will reorganize itself. Plasticity, again, is the brain's capacity or its ability to modify itself or to change itself, to reorganize itself. And a lot of times after there is some sort of damage or an injury, that it can repair itself. The video we watched in class just a little bit ago, the guy had that tumor taken out, and Carrie had mentioned there's a big hole in it. It's what do you do with that hole? Well, at some point, eventually, the brain will fill that back in as plasticity takes over and it starts to reorganize itself. But again, as I said earlier, children have the most plasticity because they're in a point of their lives where they're learning more. An example of the change is that blindness and braille users. One finger used, the sense of touch will actually move into the visual cortex. They'll actually take over, or as this says, invades the visual cortex. Because if you can't see, you're not going to use your visual cortex anymore, so it's kind of being wasted. So the brain will actually reorganize itself to be able to use that space. Some more examples of plasticity. A violin player gains expertise. The motor area linked to the left hand becomes larger. Occasionally, however, intensely traumatic effects can alter the brain's emotional responsiveness. An example is a soldier who has experienced the atrocities of war. Oftentimes, these people have hair trigger responses, and this doesn't occur until after they come home and after they've had their experiences. All right, that can change literally the biology of their brain and how they react to things. Together, the information tells us that the neuroplasticity can produce changes both in the brain's function and in its physical structure as a result of the experience. Which brings us all the way back to full circle with what we started with, and that everything that is psychological is biological. Okay? And that's just something to make sure we keep in mind. So, anyways, hope you all have a great weekend, and we will begin some other work on Monday. Just make sure you watch this video, and we'll catch you on Monday. Peace out.